Welcome to The Explainer. Today, we're diving into something that honestly sounds like it's straight out of a sci-fi movie. We're looking at a completely groundbreaking piece of research from Stanford University and Google. The paper is called Generative Agents, Interactive Simulacra of Human Behavior. And we're going to unpack exactly how these researchers managed to bring a completely simulated, autonomous human society to life, right on our screens.
To really set the stage here, I want you to ask yourself a quick question. What if simulated characters actually remembered you? If you've ever played an open-world video game, you're probably pretty familiar with how clunky non-player characters, or NPCs, can be. You can literally save their entire village from a dragon, and 5 minutes later they'll greet you like a total stranger, repeating the exact same pre-recorded line of dialogue. But today, we're looking at the holy grail of interactive computing. We're talking about computational agents that actually live, remember, reflect, and socialize in an incredibly believable way. Here's our roadmap for today's explainer. 1. Creating believable AI agents. 2. The problem with LLM memory. 3. The generative agent architecture. 4. Emergent behavior in Smallville. 5. Measuring agent believability. And finally, 6. The future of AI societies.
All right, let's jump right into section 1, creating believable AI agents as interactive proxies of human behavior. So to build these interactive proxies, the researchers started with a sandbox environment that looks a whole lot like the game The Sims. They populated this little world with 25 entirely unique AI agents. And these aren't just roaming sprites mindlessly bumping into walls. These characters actually wake up, they cook breakfasts, they head off to work, they paint, they write, and they autonomously interact with each other. The crazy part is there are absolutely no pre-programmed conversation scripts here. Every single thing they do is generated on the fly based on their environment, their unique personalities, and their ongoing interactions.
Moving on to section 2, the problem with LLM memory, and why single point-in-time generation just isn't enough. Now, you might be wondering, if large language models like ChatGPT are so smart, why can't we just plug them directly into a game? Well, let's compare traditional game logic with generative agent logic. Traditional game logic relies on rigid, manual scripting. If the player does X, then the NPC says Y. It's finite, and let's face it, it's pretty easily broken. Generative agent logic, on the other hand, requires dynamic memories. Think about it. A true proxy of human behavior has to handle constantly growing, cascading memories. An LLM alone has a limited context window. It simply cannot remember everything a character has ever done, seen, or felt over months of simulated time without becoming completely overwhelmed and totally losing the plot. To really grasp the sheer scale of this memory problem, let's take a look at the physical space these agents inhabit, a town called Smallville. It's got a cafe, a bar, a park, a college, houses, the whole shebang. An agent walking through this sprawling environment has to maintain context at all times. If an agent turns on a stove in their kitchen, walks over to the cafe, and then comes back, they need to remember that the stove is still on, and the environment needs to reflect that it's now burning. They have to simultaneously track specific rooms, objects, and complex relationships. It is a massive computational puzzle. Which brings us to section 3, the generative agent architecture. This is how these agents actually remember, reflect, and plan. So how did the researchers actually solve this massive memory bottleneck? We can break their methodology down into a super clear 3-step flow. Step 1, the agent perceives its environment and saves that observation into memory. Step 2, when deciding what to do next, it retrieves the most relevant memories and reflects on them to form deeper insights. And step 3, it uses those reflections to plan its next move and finally act. It's this beautiful, continuous input process output loop that completely stops the AI from freezing up or just acting randomly. The absolute foundation of this entire system is what the authors call the memory stream. You can think of this as a highly detailed, time-stamped database of literally everything the agent has ever experienced, recorded entirely in natural language. So if Isabella cleans the kitchen, that observation goes straight into her memory stream. This is absolutely crucial because this database is what prevents the agent from instantly forgetting what it did just 5 minutes ago. Now here's where it gets really clever. How does the agent decide exactly which memories to pull from that massive, overflowing stream? Well, the system calculates a retrieval score based on 3 specific variables: recency, importance, and relevance. Let's use a quick analogy. If someone asks you about your crush, you aren't going to suddenly recall what you ate for breakfast last Tuesday, right? No way. You're going to recall your most recent, highly important, and deeply relevant conversation with that specific person.
The architecture does the exact same thing mathematically. It scores memories to feed the LLM only the absolute most crucial context for that precise moment. But as we know, having raw memory just isn't enough. Humans learn by reflecting, and it turns out so do these agents. Imagine a reflection tree for an agent named Klaus Mueller. Down at the very bottom, we have his mundane daily observations. Things like Klaus reads about urban design, or Klaus talks to a librarian. Periodically, the system takes these raw observations and synthesizes them, bubbling them up into a higher-level realization. So Klaus doesn't just hold a list of his reading habits. Through reflection, he deduces a core personality trait, realizing, wow, I am highly dedicated to research. This is a total game changer because it allows the agents to generalize and make surprisingly human-like, long-term decisions. Let's pull back and see how this all builds together into the full system loop. The agent perceives the world, writes it to the memory stream, retrieves relevant data, plans its schedule recursively, and then acts. That recursive planning part, it's vital. It means an agent doesn't just blindly say, I will work all day. Instead, it breaks it down. I'll work for an hour, I'll take a coffee break, and then I'll resume. And if it happens to bump into a friend during that coffee break, the architecture allows it to pause its plan, react dynamically, have a quick chat, and then replan the rest of its afternoon. It's fluid, just like real life. All right, moving into Section 4, Emergent Behavior in Smallville. What happens when these autonomous agents coordinate and socialize? Seriously, what happens when you drop 25 of these autonomous agents into a town together? Well, the results are honestly kind of magical. On one hand, you might see an agent like John Lynn engaging in a highly logical, routine morning. He wakes up, brushes his teeth, catches up with his son, and heads off to his pharmacy job. But on the other hand, you see the real power of the system. Complex coordination. A user gave a single, simple prompt to Isabella, telling her she wanted to throw a Valentine's Day party. Isabella then autonomously spent the next 2 simulated days inviting people, asking a friend to help decorate, and coordinating schedules. And the craziest part, the attendees actually remembered the invitation and showed up at the right time. We also saw this incredibly natural diffusion of information. For instance, the researchers introduced just a single seed fact to one character, the fact that Sam Moore is running for mayor. Over the next few days, entirely through autonomous, unscripted interactions, that gossip spread like wildfire. Characters started forming their own opinions on Sam, they debated his local policies, and the town naturally developed a collective awareness of the upcoming election. And again, this happened without the researchers hard-coding a single interaction.
Let's look at Section 5, Measuring Agent Believability. How did they evaluate this memory, reflection, and planning?
To actually prove this complex architecture works, the researchers conducted a really rigorous evaluation. They literally interviewed the agents after a few days of simulation. They asked them a series of questions designed to probe 5 key areas. Did they maintain their self-knowledge? Could they accurately retrieve memories? Could they generate logical plans for the future? How would they react to unexpected situations like finding a burning stove? And could they demonstrate higher-level reflections about their relationships with others in the town? The results from these interviews were absolutely stunning. They ran what's called an ablation study, basically turning off parts of the AI system to see what would break. As you'd expect, the full architecture scored the highest in believability. If you remove the reflection module, the score drops. Remove planning, and it drops even further. But here is the real kicker. The full AI architecture actually outperformed human crowd workers who were paid to roleplay the exact same characters. Think about that. The AI was genuinely more consistent at staying in character and accurately retrieving local lore than actual human beings. Now, to be fair, we have to talk about the limitations. The system isn't perfectly flawless. Sometimes, agents experience memory retrieval failures, pulling the completely wrong context for a conversation. Occasionally, they'd hallucinate some pretty funny embellishments. Like one agent randomly claimed a local neighbor was the author of the 18th century economic text, The Wealth of Nations, which obviously isn't true. Also, because they're powered by standard instruction-tuned language models, the dialogue between casual friends often sounded just a little bit too formal and perfectly polite. Finally, Section 6, the future of AI societies and their massive impacts far beyond the sandbox. Once this technology leaves the Smallville sandbox, the practical applications are huge. Imagine using these highly believable agents to create safe rehearsal spaces. You could literally practice a difficult conversation, like asking your boss for a raise or navigating a tough interpersonal conflict, with an agent that reacts exactly like a real person would. Designers could use them to prototype entirely new social media platforms, observing how fake users interact before launching it to the public. Ultimately, this architecture is paving the way for social robots and ubiquitous computing systems that genuinely understand our long-term context. Let's rapidly recap what we've learned today. Large language models on their own really lack long-term coherence. But when you wrap them in this clever architecture that combines a natural language memory stream, sophisticated reflection, and dynamic recursive planning, you completely solve that problem. The end result is a vibrant society of agents capable of emergent, highly believable social behaviors. Agents that can organically plan parties, spread town gossip, and build real relationships. I want to leave you with a provocative thought to ponder as we wrap up. As this technology matures, what are the ethical risks here? We are looking at perfectly believable human simulacra. What happens when humans begin forming deep parasocial relationships with AI agents that literally never forget a single detail about them? Or worse, what happens if this architecture is co-opted by bad actors to launch highly tailored conversational persuasion campaigns? It is a fascinating yet undeniably daunting frontier. Thank you so much for joining me on this explainer, and I highly encourage you to go read the full paper to explore the depths of Smallville for yourself.